Welcome to this lecture on parasitic array. Actually, arrays in which not all of the elements are driven is called parasitic array. An uniform array, if I want to excite that, I need to have a proper feeding arrangement for every element with different phase and amplitude excitations as required. Now, instead of that, instead of driving all the elements, a parasitic array is fed by only one radiator, and there we can put some other parasitic radiators to give it a good directivity. Now, this may work, may not work. So, some of the people have found out some of the very good designs where this simple structure can work. One of that is a very famous Yagi-Uda array. Actually, Yagi and Uda, they are two scientists, Japanese scientists. They found out one such parasitic array, which is almost everywhere used for HF. HF means 3 to 30 megahertz, then VHF 30 to 300 megahertz, and UHF, that is 300 to 3000 megahertz, 300 megahertz, megahertz. TV transmissions. TV transmissions initially was in this zone, then it became here. So, in all these cases, the application is TV transmission. For TV transmission, this is an excellent antenna, and it gives good amount of directivity, which was not possible for a single dipole. So, this structure is, to understand this structure, let us look like this. Suppose I have a dipole antenna and this is a parasitic one. So, let me point out that this is one is a parasite, I am not driving it, the 2 is a driven element, this is driven, as seen that I am having a feed here driven, and this spacing is, let us take D. Now, so this is the 2 element array. What is the array axis? This is the array axis. This is one element, this is another element, and my thing is I take this driven one as a reference, and this angle is my psi angle. Okay. So, this is the array axis, 2 element array, this is my observation thing. Now, this whole thing you see I can view as a 2 port network, this is one port, this is another port. So, I can write that there is, obviously I am exciting it, so there is current here. Now, since this is nearby, this radiator 1, because this is the conductor. So, some of this radiated field that will induce here because of mutual coupling between them, and that will also induce some current here. So, I can write that what will be the voltage at port 1, this is my port 1, this is my port 2. So, V 1 will be Z 11 I 1 plus Z 12 I 2, and V 2 will be Z 21 I 1 plus Z 22 I 2. Can I write this for a 2 port network? And this element 1, it is not driven. So, I can make that the voltage, this voltage will be 0. So, now I can solve for this I 1 and I 2. So, what will be I 1? I 1 will be minus J 1 2 V 2 by Z 1 1 Z 2 2 minus Z 1 2 square, and I 2 is equal to Z 1 1 V 2 by Z 1 1 Z 2 2 minus Z 1 2 square. Okay. So, there will be radiation from both of them. It shows that even if I do not excite these, but due to mutual coupling between them, which is nothing but this Z 1 2 and Z 2 1, we were not earlier considering these, but in practical cases this is there. So, I 1 and I 2 both having currents. So, both will now radiate. So, my any far field radiation will be sum of them. Now, from that I 1 I 2 I can write that I 1 by I 2 is minus Z 1 2 by Z 1 1. Okay. Now, these two are complex impedances, because these are self impedance of the first antenna, the first radiator, by the mutual impedance of the this radiator when it is driven by 2 Z 1 2 with the minus. Now, this I can write as minus magnitude part and some phase part, because this is basically the mutual by these. Obviously, this will depend on the separation of the two, because this mutual thing is dependent on what is the separation. That is why I have taken with some proportionality constant alpha. Okay. So, this is the phase of this ratio in this. Now, can I say that the field array pattern will be what? Can I say that this is my reference, the 2 is my reference, you see. So, 1 plus this I 1's radiation, that means 1 minus Z 1 2 by Z 1 1 e to the power j alpha d minus j k naught d cos psi. Can I write this? Because there will be space phase between the two. Okay. So, this is the array pattern of this 2 element array. Now, I want that in this direction I should have maximum radiation in this direction. That means that psi is equal to 0, because wave will come from here, I will get it. So, I want this as an end-fire thing. So, to get maximum radiation at phi is equal to 0 direction, what we require? We require that this part should be how much? Alpha d minus k naught d should be equal to plus minus phi. Can I say that? Because then this part will go alpha d minus k naught d. So, that gives me d is equal to minus plus pi by k naught minus alpha. So, if we choose D like this, we can get maximum radiation in direction. Also, if we now impose that we want that it should have maximum here and in this direction it should have null. In this direction, in the back direction, it should have null. So, what is the condition? That means, we want to suppress the radiation in the backward direction. So, to suppress backward radiation I at pi is equal to pi direction, we require alpha d minus k naught, we require alpha d plus k naught d, because that direction. So, cos phi is minus 1. So, plus k naught d should be either 0 or 2 pi, and also I want Z12 by Z11 magnitude should be 1. Both should be simultaneously satisfied. Simultaneous condition if I want to produce back. But this second condition is not possible, because the self impedance and the mutual impedance is always much lower than self impedance. That is why we were earlier neglecting it, and this condition we cannot meet. So, there will be some radiation, but we want minimum radiation, we cannot get a null. So, complete null is not possible in the backward direction. So, now this is, as I said, that ideal. So, for ideal irregular array, we should have D should be, these people have found from experiment, alpha D is equal to minus pi by 2 and Z12 Z11 is equal to 1, but this is not made. Now, if we take D is equal to lambda naught by 4, this results in very small Z12 becomes small, and if Z12 is small, that means the current in the parasitic radiator is quite small, and so people took that this smaller than, generally the D is taken a bit smaller than lambda naught by 4. Now, with proper, so what are the design parameters? Design parameters are this D and also the length of the dipole, that is also another parameter. With that, in this 2 element array, you can get a directivity of 3 can be achieved. Now, if the parasitic element is shorter than this resonant length, that means I can say L1 is less than lambda naught by 2, then it acts as a director and maximum radiation occurs in the direction. That means, people have made a structure like this, that suppose I have a, this is the driven element, this is a, this direction I do not want radiation, this is a parasitic element, and here I have a shorter element, shorter than lambda naught by 2. So, these one will improve the radiation. These are called directors. People take, may take several of these elements, even their sizes may vary, that people arrive at. This one is the driven element, this is a lambda by 2 dipole, and this is a this is called reflector. So, this reflector suppresses the radiation in the back side, and these directors improve this. So, actually if I call that, let us say this is called -1 element, this is called 0 element, this is called 1, 2. So, let us in general I can have n number of directors. So, then we can write this now becomes an n plus 1 port. So, you can see that we can write the n port Z matrix like this. So, the design problem is choose the spacing di and element length li such that the currents II will have the proper phase to provide in phase addition to the radiated field in the forward direction. But since all these adjustable parameters are interrelated, it is difficult to solve, but people have write some empirical programming things. So, these programs are available in some books, these are given. So, also these are available in internet, these problems. So, by that you can have these. Now, the serious problem of this parasitic array is that the radiation resistance, if we look at this dipoles terminals, the driven dipoles terminal, that becomes quite less. It is not the 73 ohm that we get for a dipole. That is because some of these energies, they are not radiated, they are getting abstracted by these directors and reflectors, etc. So, it has been found that the reduction of radiation resistance with a spacing of 0.1 lambda naught for a single parasitic element is by a factor of 0.15. So, radiation resistance gets reduced by 15% if we have a spacing of 0.1 lambda naught thing. If we have a spacing of 0.5 lambda, this reduction becomes, I will say 15% reduction, 30% reduction, etc. So, typically for a Yagi-Uda array, the radiation resistance of the dipole is something like 20 ohm. So, quite small. Another problem is the frequency band of operation. Usually the frequency band of operation does not exceed 2 to 3% because of the required critical tuning of the parasitic elements for optimum results. Typically we can say some values which are used by designers. So, driven dipole length is 0.45 to 0.49 lambda naught. Director's length is 0.4 to 0.45 lambda naught. You say typically less than 0.5 lambda naught. Reflector length is greater than 0.5 lambda naught. So, that is why if you see an Yagi array, you can easily identify the reflector and the directors by this, that reflector is the maximum of the lot, the driven dipole you can always identify what the feed is given and director. So, by that you can find out in which direction radiation is taking place. Radiation is in the direction of the directors and suppressed in the reflector direction. Then director spacing, that is typically 0.3 to 0.4 lambda naught, and reflector spacing, that is 0.25 lambda naught. Now, the directors are not necessarily of the same length and dia, various designers use different thing, and it has been found that more than one reflector does not change the radiation characteristic. So, usually in most of the design there is only one reflector, and for directors it has been found that you can increase that number of directors, that increases the radiation performance, but beyond a certain point or beyond a certain number of directors, induced current in that director is so small that its contribution to radiation becomes negligible. Usually the designers have 6 to 12 directors. So, array length is typically 6 lambda naught and gain is typically 5 to 9 per wavelength. So, typically that comes to 30 to 54, or in dB terms 14.8 to 17.3 dB, which is quite good. Actually, that is why if you in many TV applications it becomes that you put a single dipole, you are not getting the reception, but the moment you get, because it is making your gain quite large compared to a dipole, and that gives you this. Now, important radiation characteristic of this Yagi antenna is forward and backward gain. So, gain in the backward direction also how much reduce you can do. Input impedance, bandwidth, front to back ratio, minor lobe level, etc. Okay. So, this is a good example of an empirical design, and then finally, we will see another array that is called log periodic array. This is a interesting array. Actually, it is called broadband array, but in modern times we do not call it broadband. Earlier people used to call it broadband. Actually, broadband has a connotation that if an antenna is broadband, then I will be able to pass a pulse through it, but there is another way of calling broadband, which earlier people used to call, that suppose I am having a narrowband signal, I am sending that, with the same antenna another narrowband signal at some other frequency I am sending. So, the lowest narrowband frequency signal and the highest narrowband frequency signal, if this is sizable, people used to call it broadband. But the problem is this type of broadband antenna where I have several narrowband signals can be sent, they are dispersive in nature. If I send a pulse to them, it needs that simultaneously all the frequencies need to be passed. That cannot be passed by this log periodic array. So, it is a dispersive array, that means there are dispersion if I try to send a pulse, but if I try to send narrowband signals, then over a very large bandwidth it can pass that signals. So, with this a thing I can say that these arrays are called in that sense broadband antennas. They can be made to operate over a 3 to 1 frequency band. This means that highest operating frequency and lowest operating frequency, that means f upper by f lower is 3. Now, what is the concept? The concept was actually this was Professor Ramsey used to work on this, and most of the concepts are for him. His concept was that build a structure that can scales itself up periodically as the frequency gets changed. Suppose his point was that this angle is alpha. I have two silhouettes, and now there you see his point was, suppose an antenna is operates satisfactorily at a wavelength lambda naught. So, the point is it will also perform at a wavelength lambda 2 if the dimension of this first one is changed by a factor of lambda 2 by lambda 1. Suppose one antenna operates over a frequency, means inverse of that wavelength over a certain wavelength, let us say 3 meter it can do. Now, the same antenna can do a 2 meter wavelength if I scale its dimension by a factor of 2 by 3. That was the idea. So, what he suggested, that suppose I have a structure like this, that means it is a angle alpha, and here suppose I take a element. Now, you see if I take an element here that is getting scaled, suppose I call it n plus 1th element, I call it n element, then this is n minus 1, this is n minus 2, and let us say that this length is ln, this length is ln minus 1, and this distance is x n plus 1, this distance is x n, etc. Now, so you see a continuous infinite array of dipoles. Now, what are the parameters of the dipole? Parameters of dipole are length ln, diameter an, distance, this is diameter, this is length, distance from apex, and dn is the inter element spacing. So, that means this is dn, this is dn minus 1, etc., etc. Now, if we relate that x n plus 1 by x n is equal to L n plus 1 by L n is equal to d n plus 1 by d n is equal to a n plus 1 by a n is equal to a parameter tau. So, you see the array is completely defined by this parameter tau and one of these, or I can say tau dn by 2 ln or alpha, alpha also can define any two of them. So, this parameter is called sigma. So, tau, sigma or alpha, any two of them can completely define this array. So, if we multiply all dimensions of the array by tau, it scales itself with element n becoming element n plus 1. So, the array will have the same radiating properties at all frequencies that are related by a factor tau. That means, suppose the first one here or so this side, suppose this one is f1. So, this one will be tau into f1. So, if this array operates satisfactorily at f1, then it will also operate at f2 is equal to tau f1, f3 is equal to tau square f1, f4 is equal to tau cube f1, etc. So, actually we can note that what is ln f2 by f1, that is tau, ln f3 by f1, that is tau, ln tau square, that means 2 ln tau, ln f4 by f1, that will be 3 ln tau. So, tau is called the log period, you see this. So, in order to obtain radiation from the array, it must be excited by a feed system. So, generally people feed it that this. So, there will be feed here. Now, the same feed is given here and this one is given 180 degree feed. That means, if there is a transmission line here, so one end is connected here, the same end now goes and the other one is transmission lines, other end connects here. Okay. And now, this one goes to the next one and this one goes to next one. By that, each one is having an 180 degree phase shift. It has also been found that at a given frequency, the currents in all elements except those that are close to lambda by 2 long are very small. That is obvious, because actually what is happening, at a particular frequency only one structure is resonating. So, that one is having sizable current. So, that is why and others are all having high impedance, high reactive impedance. So, that is why currents are not large there. So, that is why it is possible that though this structure is infinite, we can, depending on our lower and upper things, we can terminate it. Suppose I want some frequency, so I take few smaller ones, suppose higher frequency, so extra few elements, then I truncate it, and this side the lower frequency, so extra 2, 3 and truncate it. So, this is a finite structure. because it does not matter, because others are not resonating. So, that is why you can have a frequency band, and over that the antenna is resonating. So, it shows that when tau is typically 0.96 to 0.8, we get, suppose this one gives you this antenna gives you a gain of 12 dB, and for this it gives a gain of 8 dB, etc. And typical values of the other parameter sigma, that is 0.18 to 0.14. So, you can have that, as I said, that after truncation you can have that from tau nf frequency to tau some other n plus m f. So, these are the highest and lowest frequency components, you can say f1, f1. So, this ratio typically you can get 3:1, that means tau m is of the order of 3. Okay. So, this log periodic structure was an interesting concept and various things. Actually, if we remember the Cornu spiral from our engineering mechanics days, that is also a log periodic structure. So, equiangular spiral antenna, actually that is a circular antenna, but that also scales from the same principle. That means, where instead of length etc., you define the structure by an angle. All those can be used as a log periodic antenna. So, this ends the array. So, how to make a array broadband in the dispersive sense, that we have seen. Later, when we will see the modern antennas, we will see that the antenna that overcame this problem of broadband and which make it truly non-dispersive broadband, that is called impulse radiating antenna, which was invented in the first decade of this century. In 2005, around that time, it was invented by D.B. Giri and Carl Baum. So, that actually was the first in the history of antenna that made this contribution, that broadband, but really non-dispersive broadband, so that you can send a pulse directly to that, whereas these broadband antennas you could not send a pulse, but if you have various narrowband signals over a long frequency band, you can try to send all of them together through this antenna. Thank you.